Yeah, so our main goal is to reduce the cost of LLM evaluation, so to make the evaluation as efficient as possible. And to do that, we just try to shrink existing benchmarks. So like benchmarks with thousands of questions, we try to get very good estimates of the performance of LLMs in these benchmarks.
So are there redundant questions, basically?
Exactly. Okay. So we get rid of redundant questions and keep just like a core set of questions. So like there's a brief introduction about LLM benchmarking. So nowadays we have out there many LLMs. We want to measure them and rank them in some way so that for the user it's clear which LLM they want to choose for their specific task. So after we like compute, we give like questions to those LLMs. We compute like an overall score of this LLM, and then we are able to rank those LLMs based on this overall score. So basically, this is like a very summary of LLM evaluation with benchmarks. So usually we ask some questions to the LLM for given a prompt, and the LLM is gonna give you some response for this question. Here we have a biology question. The model is going to give some response, and then we are able to see if the model gets the question correct or not. So if we do this with many LLMs and many questions, like the data we get is a table like this. So in the rows we have different LLMs. In the columns we have different questions, and each one of these entries are gonna give you like a score if the model gets the question correct or not. But what we really care at the end is just the final column, which is like the average of all columns. And this is gonna give you like the overall accuracy of the model across questions. The problem is that this matrix is very wide because there are too many questions, you can see here. So what we want to do is compress this benchmark by eliminating some redundant like columns. And the way we do it is here at the bottom row. So we have some steps to do that. The first step, we use like a training set. We assume we have some training set, like some past data or LLM evaluation. And we fit this model. So this model is going to give me the probability of model L getting question I correct or not. So this is just a logistic model. And this model has 3 weights or 3 parameters, which are theta L. So theta L just represents like an embedding for each one of the LLMs. So this is going to give you like what are the LLM abilities. And we also have 2 parameters for each question. So one of the parameters is alpha. Alpha is going to give you like what are the needed abilities for the model, for the LLMs to get this question correct or not. And beta is just a hardness parameter, how hard the question is. So here from our formulation, you can see that if theta aligns with alpha, this is going to be very high. So it means that the score, like, it's more likely that the model is always going to get questions. If this is orthogonal or like they are pointing to different directions, so you can see that the LLM is not going to get this question correct. And this also depends on the hardness parameter. If this is very high, the probability of the model getting the question correct is smaller. If this is low, the opposite. So we fit this model using a training set, and then we want to cluster questions, so we can like basically eliminate what are redundant questions. To cluster questions, we represent each one of the questions with some embeddings. So as embeddings here, we just combinate alphas and betas. So we do that with every question, then we are able to cluster the questions by this similarity. So if the 2 questions, for example, are very close to each other in terms of these embeddings, it means that they are measuring the same thing and they have the same level of difficulty. So we don't want to keep those. So we basically cluster those questions and select a core set like of representative questions. So from thousands we can go to 100 questions. Well, step 3, we have already like this core set. So if you want to evaluate a new LLM, you give this new LLM this core question. So let's say 100 questions. The LLM is going to respond this 100 questions, and you're gonna get like a correctness vector, which is like a binary vector if the model gets these 100 questions correct or not. after we get this correctness vector for a new model, we can basically fit the theta for this new model, and we're gonna have we're gonna estimate the abilities of this new LLM. And to fit this parameter, like keeping this other fixed, we get this retraining time. It's basically running a logistic regression, so it's very cheap. At the first step, we estimate accuracy using this estimator. So this is just an estimator for the conditional expectation of the accuracy given all the questions that we give the model. So we see we know the response. And this is just a convex combination of what, like an average of what we see and what we don't see, but we can predict using this model. And here we have some main results for one of the benchmarks. So for MMLU, we have around 14,000 questions, but we show that we are able to get very good estimates of the accuracy of the models using just 100 questions. So that's why we have 140 savings here, time savings. So that's it.
Do you think companies in the industry could start using this right now, actually?
Sure, yeah. So we actually have, some people that they are using this tiny benchmarks that we made available. For example, during training, so they can track the performance of models very efficiently.
Cool.
Yeah.
Thank you.
Thank you very much.